All right, recording has started. So today's Tuesday, March 22nd, and I'm going over this page with you guys. You remember yesterday, I did a PowerPoint with you guys on thermodynamics. We went over a bunch of thermodynamics concepts. One of the important slides that we went over. Oh, by the way, I just started the Stirling engine. Yeah, let's see if I can put this on the overhead where the camera can grab this real fast. Got my own Stirling engine spinning right here. Now remember how this is spinning is because I have some hot water in this mug underneath, and there's a temperature difference. So there's this hot sink versus the cold sink. The cold sink is the room, got a temperature difference. We went through ideal gas law, hot temperature causes air to expand, cold to contract. So there's a cyclical process, and there you go. There's thermal energy turned back into mechanical energy. So leave that running. That might go for a while. Okay. One of the important slides from yesterday was this phase change. So here's the story of phase change. Both you guys do this a long time, so you guys have a really good mental model that we're going to be using today. Say you take an ice cube out of the freezer. It's like negative 10 degrees Celsius. Throw this on the stove. Right, so by putting on the stove, of course, I'm adding heat to it. So adding heat is moving left to right on this graph. Okay? But it steps up in kind of a funny way. It's going to go through a 5-part process to, well, if you're like heating the steam at the end. Okay? So first the ice has to melt. So great, I'm adding energy to it and it's increasing temperature. Increasing temperature on this graph is going up. Okay? When it hits 0 degrees Celsius, it stops changing its temperature. Now it's still, that block of ice is still absorbing heat energy, but it's going through a melting phase. So it's stuck at 0 degrees Celsius. So here is melting, right? When the entire ice cube is melted, at this point now it's 100% water, but still at 0 degrees Celsius. Now the temperature can start to rise. So going left to right on this graph. We're always going left to right on this graph. That's okay. Now the temperature's rising. When you get it to 100 degrees Celsius, the water begins to boil. Now it's undergoing another phase change. And again, the temperature gets stuck, this time at 100 degrees Celsius. Well, as long as you're at 1 atmosphere. So down here at sea level, that would be true for water. Okay. Then when now boiling sometimes is called a cooling process, not because it's cooling anything around it, like the opposite of it, but because the process of boiling, well, there's a flame underneath the water that is adding heat energy to it, going left to right. But that boiling process is carrying heat energy out of that water system. That's why the temperature is stable during this process. Okay. Then if you can somehow keep the steam afterwards, that's this very last leg of the journey, then the steam can still go over 100 degrees Celsius. That's okay. Now, for most of the problems that we're going to solve today, we'll just be stuck on one of these legs, like, for example, like this part right here. Right? Just go like back and forth, like heating up or cooling down water. But we'll get to a problem by the end of the class period today where we're going to go on that entire journey I just told you guys about. Okay, so there's the model, reminder from yesterday. You guys saw that. So let's begin this journey. Now, my numbers are different than your numbers, but we all have the same stories going on here. So just follow along, and I think you guys are going to be all right. Okay, you guys got your pages out? Does anybody not have this page? All right, we are ready. How much heat energy? Remember what heat is. Heat is a transfer of thermal energy, right? So transfer of thermal energy. How much heat is needed to change so many grams of water? I have 50 grams of water. By the way, 1 gram of water, same thing as 1 milliliter of water, same thing as 1 cubic centimeter of water. So you take this ruler, go 1 centimeter by 1 centimeter by 1 centimeter, make a tiny little box. Okay. That would be a gram of water filled with water. We're changing it from this room temperature, say about 25 degrees Celsius, to just bring it up to boiling, 100 degrees Celsius. How much thermal energy would be required to bring it up to that point? Okay. Well, again. On this graph, we're going from, sorry, focus this projection here. Come on, focus. Okay, come on. There we go. Okay. All right, here's approximately room temperature. Because here's 0 degrees Celsius. That'd be like really cold. Okay, here's like room temperature about 25 degrees Celsius. Okay, here's boiling 100 degrees Celsius. We have to go from here to here. Okay, so we're raising the temperature about 75 degrees, 25 to 100. Okay? And we're going to add this much energy to do that. And the question is, how much energy is this much energy? Okay, so we're trying to figure out. So this is number 28. Okay, back up here. I'm going to go the increase in heat energy, delta Q, okay, so the exchange of heat energy, is equal to m C delta T. This is a formula that was on that PowerPoint yesterday. So M stands for the mass. Okay, so how much mass of water are we heating up? Okay. Delta T is the change in temperature, and C is specific heat capacity. Now, I did print you guys a bunch of numbers relating to water down here. Right? Here's the 5 parts of the journey. Right, so you guys got specific heat of ice, the latent heat of fusion of water, specific heat of water, like liquid water, heat of vaporization of water, and specific heat of steam. And the only of those numbers that we need for this particular problem is that middle one, the specific heat of water, 4.18 joules per gram Kelvin, which is a very large number compared to other materials. Water has a very high heat capacity. It's really hard to change the temperature of water. So let's solve this thing. I've got so many grams of water, 50 grams. We almost never work with grams in this class. We'll almost always do kilograms. Hold on to the idea. That might be important later, but for just a little bit of water. Got 4.18 joules per gram Kelvin. Now, the fact that I got grams versus grams here, do you guys see that the grams are going to cancel out? Okay, so that's okay. But be careful, because sometimes you'll call specific heat of water like 4,180 joules per kilogram Kelvin. So careful with the units. And I'm changing from 25 to 100 degrees Celsius. So we're going to 100 degrees Celsius from 25 degrees Celsius. So you guys see that's going to be an increase in temperature of 75 degrees Celsius. Should I have converted to Kelvin first? Oh, yeah.
What's 4.18?
4.18 joules per gram Kelvin. That is, everybody can use that number. That is the specific heat capacity of water. And where I printed it on this paper is down here at the bottom. See this 5-part journey down here for the space change? Okay, it's the middle one, it's specific heat capacity of water, which is the reciprocal of the slope of this 3rd part of the journey. Okay. All right, so got that. Okay, so I just asked you guys, should I convert it to Kelvin first? And the answer is I don't need to convert to Kelvin because we're talking about a change in temperature, not a specific temperature. Now, later on, it might be important to use Kelvin. Ideal gas law comes out, but not there yet. Okay. A change in 1 degree Celsius, is that the same thing as a change in 1 Kelvin? Yeah, because those are scaled the same. Now, they start at different places, but they're scaled the same. So let's see what I get for my numbers. 50 times 4.18 times 75. Okay. I'm looking at, thousands of joules, because I've got energy measured in joules. Okay. So I could call that like 15 point something kilojoules. Okay. Guys, if you should get something in the thousands, and then your answer choices should be like kilojoules, because you just roll back the decimal 3 places. Okay, can you guys do that? Give you guys a minute. If you need help, you can call me over. If you want to work with each other, some friends at your table. Yeah, you're right. All right. Everybody good with All right. All right. Off to a good start. Next one. Oh, okay, you all right? Oh, okay. Hey, Karen. Hey, number 32. Number 32. Water flows over a waterfall that is so many meters tall. So this is the height of my waterfall. Everybody has a different height waterfall. Hey, hang on. You know what? You guys have actually seen the story before, sort of. Do you guys happen to remember a Paul Hewitt video from last semester when we were first learning conservation of energy? There was a pole jumper, guy that jumped off a pole and down into a bucket of water below. Okay? And he was trying to show you guys that the potential energy at the top is equal to is equal to the kinetic energy right as he's about to land in the bucket of water. Okay? But then So that's just conservation of energy. And then in our context, it's called the first law of thermodynamics. Then he said, when he goes splat, well, where does all the energy go? Well, it goes into thermal energy. And he left the story right there. He said, okay, if you calculated the temperature increase of his remains and you could add up and to be equal to the initial energy. Right? Now we have a way to calculate thermal energy. Right? So the old ways of energy were potential energy, mgh, kinetic energy, 1/2 mv squared. There was energy in a spring, 1/2 k squared. And we have a new way of calculating energy, and we just did it. Right? MC delta T could be an energy exchange. Right? So we've got water falling over a waterfall at some height, and all the potential energy at the top is converted to thermal energy. Right? Once that water goes splash in the bottom, do you think the temperature rises a little bit at the bottom of the waterfall? Right? And that's what we're going to calculate. Right? Calculate the temperature increase between the top and bottom of the fall. Because the water at the bottom is going to be a little bit warmer because that can splash at the bottom. Right, so number 32. This was really a conservation of energy question. Sum of energy initial equals sum of energy final, right? Or energy exchange. So I'm going to say it's all started off as mgh, right? That's potential energy at the top. Right? And then by the time the water gets down to the bottom, it takes a thermal form, which is MC delta T. Okay. And so this on the left is equal to this on the right. And do you guys notice that the mass of the water cancels out? Because that may have been a question he had. It's like, well, how much water are we talking about? Are we talking about like a cubic centimeter of water? Are we talking about a gallon of water? Are we talking about, I mean, it is a steady flow. So maybe it shouldn't really matter how much water is flowing. Okay. And in fact, it doesn't, because boom, right there. Right, we're trying to calculate what is the change in temperature of the water. So I've got the gravity field is 9.8 meters per second squared, applied to be on Earth. The height of my waterfall is 125 meters, and for you guys, it's something else. Okay. The specific heat of water. Okay, now here's where things get tricky, and I gave you guys a hint at the end of that one. I said to use this for a specific heat capacity of water. 4,182 joules per kilogram Kelvin. Okay. See, last question we used joules per gram Kelvin, so it's like 4.18. Now it's 4,100, right? Because we have to use go back to base SI units, which is kilograms, not grams. Okay. All right. So I see one algebra step. I'm going to take that specific heat capacity and divide it down to the left side. Okay. So what is 9.8 times 125 over 4182. I'm getting a temperature rise of 0.29 degrees Celsius. And that is my answer. Yeah. Yeah, so I did 9.8 times 125, all divided by 4,180.
There you go. No, you did. Don't do it. How am I supposed to? You said you got. Oh, no. Sorry.
Is this working out for you guys? All good? Oh. All right, next question. Number 55. Hey, by the way, these numbers are coming out of your book. So there's a book on your desk if you wanted to reference the question. You could. A 50-gram piece of, mystery metal. Mystery metal. At 100 degrees Celsius, that's a hot piece of metal. Is placed in 200 grams of water at 20 degrees Celsius. At 20 degrees Celsius, approximately room temperature. The mixture reaches equilibrium at 22 degrees Celsius. What is the specific heat of the mystery metal? And that would be a property that's unique to that metal. So then you could go the further step and say like, oh, but now we know it must be like zinc or something, or copper or something, right? Do you guys notice that? Look at these temperature differences, even before I start plugging and chugging. I mean, that was a hot piece of metal, 100 degrees Celsius, and room temperature water, 20 degrees Celsius. And the equilibrium temperature, do you guys notice that the temperature of the water rose a little bit, but the temperature of that metal really plummeted a lot, right? And that's a realistic example too, because water has such a high heat capacity, it's really hard to change the temperature of water. Also, there's more mass of water, so that's another factor 2. But so both of those would be why the temperature of water barely changes, but the temperature of the metal drastically plummets. All right, so number 55. Draw you guys a picture for this one. Maybe we've got, say, a glass of water, a beaker of water, okay, drop in a hot piece of metal, and that hot piece of metal is emanating heat into the water. And my model for this is going to be, there's a heat exchange. The delta Q, the loss of heat energy by the metal,
Yes.
is exactly equal to negative delta Q of the water. Right? That's to say that the heat imported by the water. Okay, so there's an import and export of heat energy. And this is in line with the first law of thermodynamics, which is conservation of energy. The energy lost by the metal is exactly picked up by the water. Right? Energy exported by the metal is imported by the water. So I've got mass of the metal times specific heat of the metal times change in temperature of the metal is equal to, and then negative because export import, mass of water times specific heat of water times the change in temperature of the water, right? Okay. Now, change in temperature, isn't that like final minus initial? Right? So I'm gonna go another step, mass of the metal, specific heat of the metal times final temperature, which is actually what we're telling for, minus initial temperature of the metal is equal to negative mass of water, specific heat of water, final temperature, shows up there again, minus initial temperature of the water. Okay. So remember what's going on with the story. Hot metal, cold water, the metal loses heat energy to the water that cools down the metal and heats up the water. And that process continues until they reach an equilibrium temperature. That equilibrium temperature we're calling T sub F, like the final temperature. Okay? And that shows up in 2 places in this equation. Now you should have all the other numbers. So I'll go ahead and just plug in the numbers at this point, although you could solve in terms of variables. That would be an extra layer of fun. But plug in some numbers at this point. So I got 50 grams of metal myself. And, oh, you know what? I'm so sorry, guys. The setup is okay, but we're solving for something different than what I said. We know what the final temperature is. We're not solving for that. We're solving for what is the specific heat of the metal. Okay, so oops, that's okay. Because the setup is still correct. Okay. The final temperature on my page says 22 degrees Celsius, and that came from 100 degrees Celsius for the metal. Equal to, my mass of water was, had 200 grams of water. That's also 200 milliliters of water. It's also 200 cubic centimeters of water. Specific heat of water is 4.18 joules per gram Kelvin. I'm using the one with the grams in it, it's 4.18. And then the final temperature was also 22 degrees Celsius. That was the equilibrium temperature, but it rose from 20 degrees Celsius. Let's see, degrees Celsius. Okay. Okay. And it's perfectly okay to use Celsius and not convert to Kelvin because we're talking about a change in temperature. So even if I converted to Kelvin first, it wouldn't make any difference in the end because a change in 2 degrees Celsius is the same thing as a change in 2 Kelvin. Okay. We clean this up a little bit here. What's 50 times 2 minus 100? Okay. Look at that negative. I'm going to drop the units just for a moment here. Equals 200 by 4.18 by 2. All right, divide both sides by negative 3,900. Okay, specific heat of the metal is this many joules per gram Kelvin. Okay. That looks like a pretty realistic number, by the way. Okay. Different metals have different heat capacities, but yeah, that looks pretty realistic. Okay. Remember that for water, the specific heat capacity was 4.18 joules per Kelvin. And this is approximately 1/10 of that, or at least my answer is. That means it's 10 times more difficult to change the temperature of water compared to that metal. Okay. But you guys know that anyway, right? You put a pot of water on the stove, the metal part of the pot heats up real fast. That water takes a long time before it starts to boil. Okay. Give you guys a minute to get your own answers too. You guys can help each other out if you want.
Yeah, let's help each other. So,
Everything all right?
I got something similar to that.
I'm actually.
I got like 2.29, but I put 2.7.
You got.
Mine is different numbers.
You should have like. That's why I I saw more.
No, I don't need that.
Everybody get an answer for 55? You guys doing good?
I can give my friend.
Okay, next one. Number 56.
I swear.
Got a 600 gram sample of water at 90 degrees Celsius. Oops, that's some really hot water, right? Wouldn't want to touch that water. It's mixed with 400 grams of water at 20 degrees Celsius. That's about room temperature. What is the final temperature of that mixture? All right, this is going to be a pretty similar thought process to what we just did. We got hot water and cold water, and we're going to mix them together and say, what's the final temperature? So I'm going to say that the heat energy lost by the hot water is exactly the heat energy gained by the cold water. Hot and cold, right? Hot and cold. Until they reach equilibrium temperature, and then they're just like both lukewarm. So it's going to be mass of the hot water times specific heat energy of the, well, I'll say water because it's just water, right? Times temperature final minus temperature initial of the hot water is equal to negative mass of the cold water times specific heat capacity of water times temperature final minus temperature initial of the cold water, right? MC delta T. Right? MC delta T, is that okay? Okay. Do you guys see that something will cancel out? What's going to cancel out on both sides? Yeah, specific heat of the water. What that means is I could have made it any substance, as long as the substances were the same. I could have said olive oil and whatever the final answer is, as long as it's the same substance. And this time we are solving for final temperature. Okay. And this is the one that shows up 2 places in the equation. So I'll go ahead and plug in my numbers. I had 600 grams of hot water. Temperature final minus, see, temperature initial. Mine was at 90 degrees Celsius. Equals negative. Okay, and then I had 400 grams of cold water. T final minus, and then T cold was 20 degrees Celsius. Okay. All right. Once you get to that point, do some algebra. It's like solve for x, well, T final. Okay. So two places, because they're reaching equilibrium temperature. They're both going to the same final temperature. Okay. So I might distribute. Let me try this distribution method. So it's gonna look like. Drop my units just for a step here. All right, there's how mine finishes up, and I'll give you guys a minute to also get your answer, help each other out, and call me over if you need me.
I feel like it's
Use 700 grams.
I use 600.
So you should have 700 here. Right? That should be, yeah. That's where my 400 is. And then instead of 90, 20, I'll have 90.
Recalculated.
Cancel out the saves. You saw that first.
You said you know. You don't do it. What'd you get? She just doesn't want it.
I honestly don't remember.
I got like a 9.6 now. on the SAT, but I just didn't try it. My first SAT, I got a 9.72.
Oh. All right, so I think you guys are good on that one. Next one, number 57. Got a 50 grams sample of zinc, which has this specific heat capacity. Now this is implied when zinc is a solid, because at room temperature, zinc would be a solid. Right? And okay, so this is a hot piece of metal, 75 degrees Celsius. Right? Well, zinc would still be a solid. Placed in a container of 800 grams of water, which has this very high heat capacity, 4.18 joules per gram Kelvin. Which is okay. So I got some cold water, hot zinc and cold water. What is the final temperature of the water and zinc together? Okay, so kind of a combination of the last two questions. What's this? $57. Back here. Okay, so we got this beaker of water, drop in the zinc, emanates all this heat energy into the water, which heats up the water a little bit and cools down the zinc a lot, right? Although it's equal exchange of heat energy. So the heat energy lost by the zinc is exactly picked up by the water. Okay, so there's your framework. So I've got mass of the zinc times the specific heat capacity of zinc times the change in temperature of the zinc, MC delta T, that's your heat energy, is equal to the, imported by the water, mass of water, specific heat of water, change in temperature of the water. Okay. Now change in temperature, of course, is a final minus initial. And so let's go mass zinc, specific heat capacity of zinc, temperature final minus temperature initial of zinc equals negative mass water, specific heat of water, final temperature minus initial temperature of water. Now, since the zinc is cooling down and the water is heating up, at some point they're going to reach an equilibrium temperature, which means that these two guys are the same, and that's what we're solving for. So at this point, I'll go ahead and plug in my numbers. I have 50 grams of zinc, so 50 grams. The specific heat capacity of zinc was given as 0.39 joules per gram Kelvin. And seeing what's the equilibrium temperature. And I started with a really hot piece of zinc. It was like 75 degrees Celsius. Negative. Mass of water was 800 grams. 4.18 joules per gram Kelvin, specific heat capacity of water. Then final temperature minus, it had some pretty cold water. It was at 10 degrees Celsius. Just here. Okay. Let me try the distribution method again, just like I did for a recent problem. Distribute. Okay. See what this is going to look like. It is 50 times 0.39. Oh, okay, times TF. So okay, 19.5 TF. I'm going to drop my units just for this line. Minus times 75. So one line is going to look like that. Combine the t's, combine the constants. Divide by the coefficient in front of the t. And you get your equilibrium temperature. that looks like a believable number. Okay. Of course, that's always a good check at the end of any math or science problem. Make sure that the answer looks believable. Now, why do I say this looks believable? Well, because the initial temperature of the water was 10 degrees. And so the equilibrium temperature is like 10.4 degrees. Okay, so the temperature of my water budged up a little bit, but hardly anything at all, versus the temperature of that zinc really plummeted. And that's for two reasons. One reason is that I had 8 times more water than zinc by mass. But the other reason is that water has a huge heat capacity compared to zinc. Right? So it's like more than 10 times what zinc is. Okay? So it's really, really, really hard to change the temperature of water. Easy to change the temperature of metals. Okay, yeah, this is an answer choice on my paper, so I'm good. So I'll give you guys a minute to help each other out. Make sure you guys get your answer too.
It's gonna be more.
It's gonna be it's gonna be around the same position.
Yeah, so it's gonna be more. But this is low. This is low. Yeah, this is low. Yeah. So yeah, everything's more sensitive, more stuff is on. I think this
All right, so everybody ready?
Oh, I guess.
Um,
So we do.
We're going left or to the right. So I think I 33, 44.
Oh, I think they're all right.
So you said all. Oh, he has how to do it right.
All right, let's do one more today. Let's do number 64. Okay, ready for number 64? This will be our showstopper. How much heat energy is needed to turn so many grams of ice? I have 11 grams of ice at -10°C into steam at over 100°C. Mine says 120°C. Okay? Okay, so let me give you guys some context from this graph. Okay, so far we've been mostly navigating some part of this, back and forth, or for like the zinc, maybe back and forth here. It's some version of this, like. But this question, we're going from this point on the graph all the way to this point on the graph. Okay, you guys see this is going to be a 5-part process, right? 1, 2, 3, 4, 5. Right, you guys see that? And then the numbers you need for those parts of the graph for water are listed right down here. Okay, you guys see these 5 numbers? Okay, so I'm going to refer to this table of numbers. You guys see what I'm referring to? Right, for on your page. Okay. So here we go. 5-part process. So how much heat energy is needed for that temperature change? Number 64. So I'm going to go delta Q for the first leg of the journey, delta Q for the second leg of the journey, delta Q. You guys know delta Q is like the heat energy that we're adding to it, right? The third part of the journey, is to get water to get it to boil. Fourth part of the journey, which is you boil it all the way. And then the fifth part of the journey is you're heating the steam up to the final temperature. So this is going to be the mass of the water times the specific heat of ice times the change in temperature just to bring it up to 0 degrees Celsius. So that's for the ice. Okay. The second part of the journey is actually the latent heat of fusion. That's how much energy do you need to melt this thing? That's to say, basically, what's the length of this leg of the journey? What's the length of this? Right? Which would be some number of joules. Good, what we're doing. So that's M times delta H fusion. Right? Because there is no temperature change during that part of the journey, right? Right? That's why there's no delta T. Right. The third part of the journey, we're going to take the water from 0 degrees up to 100 degrees Celsius. So that's MC water, delta T water. And that delta T, of course, is going to be 100 degrees, go from 0 to 100. The fourth part of the journey is going to be that mass times the latent heat of vaporization. Okay. And the last part of the journey is we're going to take that last bit of steam, mass times C of steam, times delta T to bring it up to its final temperature. Okay, first. All right, you guys got that? 5-part journey? All right, so off to the right here. Now, each of these is going to take some amount of energy, some number of joules, and then at the end, I'm going to add up those 5 parts and figure out what's the total energy, and that'll be the answer. So I've got 11 grams of ice, so 11 grams. The specific heat of ice is 2.09 joules per gram Kelvin. And we're taking it from negative 10 degrees all the way up to 0 degrees. Isn't that a change in temperature of 10 degrees Celsius or 10 Kelvin? Because it's a change. Okay. So that's the first part. The second part, I'm taking my 11 grams and multiplying it by 334 joules per gram. Okay. That's to melt all the ice into water. The third part, now we have liquid water, but it's all really cold. It's like 0 degree water. So we need to bring it up to boil. So that's gonna be 11 grams at 4.18 joules per gram Kelvin.
Does that say
This is joules per gram. That's a unit. Okay. And we're going 0 to 100 degrees Celsius. That's a change 100 degrees Celsius. All right, then we need to boil all the water away. So that's 11 grams. And the heat of vaporization is, see, what's to say, 2,260 joules per gram. 2,260 joules per gram. Of course, the grams cancel out. And then finally, now we've got all the steam, but we need to heat up the steam to the final temperature. So 11 grams at 2.01 joules per gram Kelvin. Okay. And I'm bringing mine up to 120 degrees Celsius from 100 degrees Celsius. So see that'd be a change of 20 degrees Celsius. Yeah.
On the third step, do we all put up
Yes, guys, that is true. Everybody has 100 here because you're going from 0 to 100 degrees Celsius, right? Right. Got just have time to throw the calculator. What's 11 times 2.09 times 10? I'm looking at, well, you know what, I'll just do it this way. I'm just gonna add them up like this. So I got 5 different energies. I'm gonna just add them all on my calculator screen. So that plus 11 times 334 plus 11 times 4.18 times 100 plus 11 times 2260 plus 11 times 2.01 times 20. Okay. So that's 33,804 joules, or I could also call that 33.8 kilojoules. And that is an answer choice on my page, so I'm good with that. All right, got a couple minutes to the bell, so I'm gonna stop this recording, but all right, we'll do some more of these tomorrow.